Today is lecture 19, and again, just I mean, what I'm planning right now is that maybe this lecture plus next lecture we do partitions, and maybe a little bit of time might be required if we don't finish in time. And then after that, we begin a new topic called symmetric functions. I mean, it's not really a new topic, but um, I mean, this is one of those things that I thought, okay, if it's so important that you should know something about it, even though it's difficult to sort of uh, get very far in this, but this is a modern topic. So if you go, for example, if you go to a graduate course, after your undergrad, you go for a master's degree and take a course in combinatorics, this will show up, and then if you don't know anything about it, it will be a problem. So for that reason, we'll do a few lectures of this and maybe few exercises. Anyway, so meanwhile, we are doing partitions, and today, hopefully, I will show you my advisors and grand advisors theorem, one of their theorems. So anyway, recall first what we were doing. So we are creating a calculus for finding the matrix, the frequency generating matrix. So we had some in the more easiest case, this was the matrix. And if you take an n by n matrix from here, just the and then on this side you have p of n minus 1 to p of 0, and this would give you f1n, f2n, and so on. And this, together with the fact that k fkn is equal to m npn, we can determine everything starting from p0 equal to 1. And the idea was that this is the starting point, and then the idea was take any partition generating function and get the A's so that this story can start. So now any partition generating function uh, is so we did all kinds of things. So we did things like this. Then we did things like 1 minus CQ raised per K. And then if K belongs to some set S, we also did that, and so on. So now today's task is to sort of, bring some closure to this. So we've done a lot of them. Now I want to do a lot of such products. Now, what do you do when you have a product of two of these kinds? That's the idea. So the example we have is what are called over partitions. So this is a relatively modern topic. These were introduced by Corteil and Lovejoy and studied recently. And what they are, so they, different kinds of partitions arise in different kinds of contexts. So this is an over partition is a partition of n where the first part uh, or the first occurrence of a part can be overlined. or distinguished in some way. So the sum is still n, sum of parts is still n, regardless of. So let me do an example. This is the, we use a bar here, number of over partitions. So for example, uh, this is possible. You have overlined this. This is also possible. You may not do any overlining. This is also possible. And these two are considered different. So there are, I mean, you are allowed to overline the first guy. And you're also, so for example, this is also allowed. So plus more. So let's generate it. So to generate these partitions, we use two symbols, x and y. So remember, we are using these symbols x to generate, and what we'll do is let x be used to generate the usual partitions of, let's say, k, and y you generate partitions of k with distinct parts, of n minus k with distinct parts. And we look at the x plus y. So we look at our partition should be something like this, summation I xi plus summation I yi. This will be our partition. So these y's are looked at like over partitions. These are the overlined parts. And these are the usual parts. And what we are saying is that this is a partition of k. So this is a k, partition of k. This one is a partition of k. And this one is a partition of n minus k. And this would be a partition of n. So kind of like a convolution, and that's the basic idea. So let's just list few for n equal to 4, let's say, just to get some. So here are the ones for x. So this is k. This is the empty guy. This is x1, 2x1, x2, 3x1, x x1 plus x2, x3, and 4x1, 2x1 plus x2, x1 plus x3, 2x2, and x4. So there are 5 of these. And let's look at the ones in y. And here we are starting from 0, 1, 2, 3, 4 in the other way. This is an empty one. Now these will be distinct parts. So y1, y2, y1 plus y2, y3, and 2y2 is not allowed, y1 plus y3 is allowed, y4 is allowed. Right, so the partition is, these are the partition, the over partition are given by sums of the form, uh, something here. Let's call this, I don't know how to say it. So it's called A plus B, where A is a partition, A is in this set, summation IXI, where A is a partition of K and B is a partition of N minus K, and B belongs to, B is equal to some IYI. Some iy. Right. So ultimately, for example, you'll get things like this: 3x1 plus y1, x1 plus x2 plus y1, you know, x1 plus x3 plus nothing. So this corresponds to 3 plus 1. This corresponds to 2 plus 1 plus 1. The first is overlying. This corresponds to 1 plus 1 plus 1 plus 1. You know. So all these are partitions of over partitions. So it's clear. I mean, this is clearly a model for convolutions. So clearly, k going from 0 to n, p of n with p of k with no restrictions, but then p of n minus k where restriction is of distinct parts. This entire thing will be equal to p of n. And so this let's call it q bar q, the generating function of p bar n, q raised per n over n. This will be equal to this summation, and then q raised per n, and this will be this just the generating function for partitions multiplied by generating function for distinct parts. And this we know to be 1 over 1 minus q square, so on. And this we know to be 1 plus q square, so on. So 1 plus q raised per k over 1 minus q raised per k, or in our notation, qq infinity. So is that clear that this is the generating function for over partitions?
Professor, how did we go from step one to step two? Like,
From
how
here to
did the
here?
summation? Yes, Professor.
Well, this we already know that if you, I mean, what are you doing? You're taking all these guys, each one of this and one of this.
Yes,
One of
Professor.
this and one. So if you multiply them together, this will give you the number, and then you sum
Yes,
over
Professor.
k, and you get the whole thing.
Yeah, Professor. So I am confused about the next step. Like, how are we going from summing over n of summation k is equal to 1 from there to like summation n pn q to the power n times summation n pn minus k, like the bottom step, the step below
From
this.
here to here,
No, the one below this.
from here to here.
Yes, Professor.
Yeah, so this is, I mean, this is your usual stuff, right? I mean, this is your usual convolution. So if you take any, so what do you get? You get ak bn minus k summation over k and then summation over n. This is known as Cauchy products in analysis. Oh, I know why you're confused, because this is wrong. This should be n. Okay, okay. Now is that clear?
Yes, Professor.
Okay, okay. Now I get it. Why you were saying that this is confusing. Yeah, this is wrong. That's why it's confusing. Okay, so yeah, so when you take multiply these two, you take one with k, one with n minus k, and what we had was both n minus this n minus k. But now it's correct anyway. Okay, now it's fine.
Yes, Professor.
Okay, so now how do we do the frequency generating matrix? The way we do it is let's look at uh, two frequency functions. This is the number of k's in the x part in the partition of x. Mm. So in the over partitions, there is a partition on in x, and there's a confusion because there is k is coming as that also. So this is the ordinary partition, and fky, which is number of k's in the y part of the partition. So suppose we have 3x1 plus 2x2 plus y1 plus y3, then what we are saying is f1 of x of this partition, whatever it is, this lambda, suppose this is lambda. So if I have just for this lambda, I will have 3 of x1, and fy, the contribution will be 1. So this is a wrong notation. Just say contribution to f1x is this, and contribution to f1y is 1. Right? And then you add the contributions in all the partitions. That's the idea. So in our example, we have this plus this. So if you're taking all the partitions, these are all representing partitions now, because this plus this is 4, this plus this is 3 4, this plus this is 4, and so on. So you'll add all the x1s together. So you'll have 1, then plus 2 plus 3, that's 6 plus 4, uh, 7, 8, 9, 10. So there are 10 of them. No, is it? 6, 7, 8, 9, 10, and 14. So f1x is 14. And y's are just coming in 1, 2, 3. So in our example, f1x of 4, we got 14. And f1, so y of 4, we got 3. Right? So 1, 2, 3. I mean, whatever the partition. No, actually, we get more because, hang on, this is wrong. If you do x1 plus y1 plus y2, that's one partition, and x1 plus y3. So this one will come in 2 times. So there are 2 here, then 2 here. So that's 4 plus 3, 7. And here it's fine. 7 plus 4, 11, 12, 13, and 14. Is that what I got earlier? I'm still getting 14. So I'll get 2 plus 2, 4, 7, 8, 9, 10, 11, 15. And now for y's, this one will come in 1, in 2, and this will come in 3. So 1 plus 2 plus 3 of them. So 5. That's the answer. Is that clear? Is that okay?
Yes,
So,
Professor.
yeah, so I mean, what we have is two frequency functions, and it's clear that fk of x of n will be it satisfies the same kind of recurrence. And fk of y of n, so same thing. I mean, you can get a new, if you want a new over partition with the k parts, you can add xk to the uh, the over partitions which are already enumerated of n minus k, and then get this. And then this was already there, and same thing we do with distinct. So let's take two different generating functions. So let's, in terms of generating functions nkx and nky, we get nkx of q. I don't know, this x is becoming a star sometimes. 1 minus q raised per k, q bar q, and nky of q is q raised per k, 1 plus q raised per k. And the matrix looks like, so matrix is this is a 2n by n matrix, and here you get f1 xn, f2 xn, so on up till fn xn, and then f1 yn, f2 yn, and so on up to fn yn. So what we got essentially, I mean, so in some sense, it's like you're putting both these matrices together, okay, where an1 is the matrix for ordinary partitions, and an2 is the matrix for distinct partitions. So we just, I mean, what we are getting is that if you take all the rows of the ones, and then you take all the rows of the alternating signs, and then when you multiply by p bar, this one will give you the first n ones will give you the f1x, f2x, and so on, and the next n will give you with y's, f1y, f2y, and so on. So well, the formula can be written: ai of j is equal to 1 if I is between 1 and n, and j is equal to r times I, and it's minus 1 raised by r minus 1 if I is between n plus 1 and 2n, and j is r into I minus n. So you shift basically the first n rows are repeated. So when we have n plus 1, it's the n equal to 1 case of the previous guy. So this is r and 0 otherwise. Okay, let's do an example. Let's calculate n with n equal to 4, just to see what's going on, just to convince you that it's okay. So this is equal to 1. And what are we, the first step to get n equal to 1, so we'll go up till maybe n equal to 3 or something. Okay, so the first one is just this, and then I'm multiplying by this, and then so this is the p matrix is the A matrix, and when I multiply, I'll get 1 into 1 and 1 into 1. So this is F1 X1 and F1 Y1, right? And what is P1 then? This is 1 times 1 plus 1 times 1. That's 2. So this will account for, so let's just see, you have 0 and you have x1, and then you have 0 and y1. So there's one guy will be x1, one guy will be y1, and there are two such partitions. So this is okay. Let's do n equal to 2. So n equal to 2, you'll have this. No, won't have this. You'll have 0, 1, and 1 minus 1, 0, 1. And then you have 2 and 1. Okay, so the first guy will be 2 plus 1, 3. Uh, this is 0, 1. Then 2 minus 1 is 1, and 1. Yeah. So now what is p bar of 2? This is 1 into 3 plus 2 into 1 from here, plus 1 into 1 plus 2 into 1 from here. So these are the y's, these are the x's. So that's 3 plus 2, 5, plus 7, 8. Right? So we can quickly check. For 2, so there will be 2 here, 3, 4. Oh, wait a second. This is not P2. This is 2 times P2. So this means that P bar 2 is equal to 8 by 2 equal to 4. Okay, so this is 1 times P1. Okay, so this checks out. Let's do one more. N equal to 3, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1 minus 1, 1, 0, 1, 0, 0, 0, 1. And we have 4, 2, and 1. So now you can see, I mean, it's getting more complicated, but this technique is very simple. I mean, there's nothing to it. You just get whatever you want to get. So this is 4 plus 2 plus 1, that's 7, uh, 2, 1. And then for the y's, it's 4 minus 2, that's 2 plus 1, 3. And then 1, 2, and then 1. And what is 3 times p bar 3? That is going to be 7 plus 4 plus 3 plus 3 plus 4 plus 3. So how much is that? Okay, 10 plus 10, 24. So this means that p bar 3 is 8. And this, let's calculate it again. So it's a 2x1, x2, 3x1, x1 plus x2, x3. And then for y's, y1, y2, y3. So how many are there? 1, 2, 3 plus whatever. 3 plus 4, 5, 6, 7. 8, 9, 10. So there's something wrong. What's wrong? 1 times 7.
Because it's 8 only from the table also.
Huh?
Should be 8. I think you counted wrong.
I counted wrong. How?
It's 3 1 2 3.
This was
No, 2 2 1 2 3.
this was x2. Yeah, so there are 3 here, and then 2 here, 1 here, and 2 here. Okay. 5 and 3, 8. Okay. All right. So yeah, so it works. Um, so just to summarize, what we have done, you know, we started with this guy, we did this guy, we did, suppose all the k's are not there, 2k minus 1, this guy, right? Then we said, okay, let's add a z here. We could add a z here so that it accounts for parts. We could add a z here to account for parts. And this meant that we could do 1 minus z q raised per 1 minus k q raised per k, I mean with z or without z. So you could change the signs of the z or whatever. So you could do odd minus even, calculate those terms. And now what we have done is we have multiplied two of them. And in multiplication, all we see is just, it's a 2n by n matrix. So we just add stack up matrices. So we can do all of this, and you can multiply it n times, and you can, so in sum, ultimately, which I won't do, we could do things like this. And here, vk could be positive or negative, so it goes up and down. And we can do two of them at the same time. And in fact, vk can be a complex number. And in this case, the matrix, the entries are multiplied by k, the kth row. So it's not very different from uh, the original matrix. So all of these guys are derived from this original matrix by doing something. Either you change signs, either you multiply by something, either you do alternating signs, and so on. So this matrix is a very important matrix, it turns out. And uh, I would say, yeah, so this is, I mean, almost this matrix is sort of, um, it's there, it's been studied, but this particular matrix, it's not been studied for some reason. Uh, I mean, there are some very the matrices which are very neighboring this, which have been studied, and lot is known about them. You know, one which has been studied, which has all ones and everything else the same, all ones in the first column. But somehow people have not arrived at this, and this seems to be at the heart of the issue. And uh, next time, I'm hoping that we will do. Uh, uh, so So this finishes the story for now. Next time, or I mean, before we finish with partitions, so all of you notice this, or most of you who tried this problem notice this. So we will give a proof. So this is, I'll give a proof. So our proof, which means a new proof, pretty easy one, which follows from this guy. So we'll give a proof of this using these matrices next time. By the way, I mean, you guys are nowhere close to Ramanujan, because Ramanujan found something like this also. And and he also found for 11 something, I don't know, forget what, from the same table.
Professor, I think it's 7, if I'm not wrong.
This is 7.
I'm not very sure, but I remember reading 7.
And in fact, there is some of mod 25 to something like that. So, you know, one of the very famous mathematicians, and he's so famous that I've forgotten his name. And he's a master in, I'll remember his name at some point. So he's a master in doing experimental math. And he said that, whatever time you spend in programming a problem and getting the number, spend at least that much time staring at the results. So people spend a lot of time in just experimenting, but they don't see what they have got. So anyway, so this we have, I don't have a proof of, but there are many more. This is the entire industry. Ramanujan noticed all of these, and he gave a proof for all of these. And um, his proofs are a lot more complicated than the proof that I will give. So our proof meanings I'll give with my in my joint work with Hatosh Pal. That will be next time.
Oh,
Meanwhile,
Professor,
yeah,
it's 11n plus 6. I just verified.
6. Okay, so these stories are not over yet. So there are different kinds of partitions, and you get different kinds of recurrences and so on. Okay. Now, what I want to do next is I don't know whether we'll be able to finish it this time, but we'll begin. So this is called Garcia-Milne involution principle. So I promised myself uh, that the first time I teach combinatorics, I will surely include uh, one proof of a theorem of Ramanujan, which is this, and um, one proof and one this theorem, this principle, some example of this principle, which I don't know so well. I haven't used it so much, but I just learned it today for you. And the reason is that this guy is so we are all related. He's my academic father, and this guy is my academic grandfather. So his advisor. So my advisor, my boss, and my boss's boss, basically. So it's a very famous story that George Andrews announced a reward of $100 for a bijection proving the Rogers Ramanujan identities, which also I will show you next time. And it was very tough. And then these guys in 1981 they wrote a 50-page paper where they gave which is called a Rogers Ramanujan bijection. So this was published in a journal, and it was the first proof of Rogers Ramanujan identities, which was a bijective proof. But very very interestingly, it was not a they proved a bijection can be created. So they have a program for writing. Now let me tell you a bit about Garcia. Garcia is one of the most famous combinatorialists around in the world right now. So Milne was his PhD student, and he solved one problem very quickly, and he got his PhD. And then Garcia told him, "Let's try this." While he was finishing his PhD or just after. And Garcia does all his work uh, from the beach. So he works in San Diego, He's in the University of California at San Diego. He's above 90 now. I think they celebrated his 90th year birthday last year. And any meetings which happen, you're basically supposed to take your swimsuits, and Garcia will take you to the beach, and then you do your work at the beach. So he lives on the beach. On the beach. He's a very strange guy, interesting and strange guy. And so Milne told me that this idea came just on the beach. I mean, they just kept doing. And Garcia at that time also, his first thing. So this Milne taught me, and he kept insisting, and that's what I use in my teaching and my research. He says that whenever Garcia would see a new concept, a new combinatorial concept, he would first write a program to list it. So he would do it by hand, and then he would write a program. And many times when he would do that, he would discover something new. Because to be able to, program something is almost like, so that's a way of understanding something. Okay, which is what I keep asking you guys to program. And of course, I asked you to do it in Sage. He was doing it in real weird languages where it's not so easy to represent partitions and so on. Anyway, so what we are going to do is we will show. So we will follow. So I wanted to understand this myself, and that's why I did this. And what we are going to follow is we are going to follow an exposition by Andrews. And the reason I'm presenting it right now is that these, X's and Y's play a role in understanding how it's done. So what we do is so Andrews wrote a book in 1985 where he explained this, and he basically said that let's prove a simpler one using this technique. So this was the first theorem that we proved. P of n into even parts into odd parts, and this was basically this guy, right? So distinct parts was this 1 plus q raised per k over k. So this was distinct parts, generating function for distinct parts. And one can write it as we can multiply and divide by 1 minus q raised per k. And then this gives us, if you cancel the even terms from the bottom, you'll get the odd parts. So what Andrews does is, and so what Andrews is doing is explaining this proof of a Rogers-Ramanujan identities, and somewhere in the proof you use this so-called involution principle. So now, in fact, in textbooks it's just called involution principle because it's become so central to combinatorics. So it's like principle of inclusion exclusion. So involution principle comes in that level now. So the Garcia Milne has disappeared in modern day textbooks. But since they're related to me, I like to use their name. Okay, so what they do is they look at this guy. They look at the set of uh, uh, partitions generated by this guy, and here what we are looking at is, again, we are looking at a convolution. So we are taking two products and you're multiplying them together. So just like we did for over partitions, we look for these two products, and this generates ordinary partitions, and we are going to generate them by x. And this is that odd and even kind of guy. So let's just look at partitions uh, with only distinct and even parts. So I'm not looking at this actually. I'm looking at uh, 1 plus q raised power 2k. And then I will put some sign over here. So I'll put a sign here. Okay, so we break it up. We put a sign over here somewhere later on. And so again, x and y, this will be generated by y. So we look at partitions of the kind summation I alpha I xi. Actually, I don't know why I was writing I xi. I should be writing alpha I xi. It was a mistake. I never wrote it. I think I wrote it and I think it was wrong. Yeah, this part should be alpha I beta. Sorry about that. So please correct. Yeah. So we are looking at this guy where this is just 2i, and in fact these beta i's are all 0 or 1, and these are all of them. So only even parts, okay, right? And we want to do some kind of a sign reversing involution. So but first let us just list it again. For n equal to 4, let me list it. Let's list these partitions just to get some idea of what's going on. So this is for x's, 2x1, x2. Like I said, you have to do the same thing repeatedly many times when you're doing. That's why you become an expert, becomes automatic. X2 and x4. It may become automatic, but you still make mistakes. Okay, and then so this is k, sorry. So we're doing n equal to 4. And then with y's, let's start with empty here. And this is k equal to 1. There is nothing here. K equal to 2. Yeah. So y2 is allowed. So only even parts and distinct parts. And k equal to 3, nothing here. I mean, this should be really nothing. This is still an empty partition. And so what is it? K equal to 0, 1, 2, 3, 4. So 3, there is nothing. And 4, there is, well, there is, it has to be distinct. So 2y2 is not allowed. So y4 is there. Right? So 2y2 is not allowed. Right? So there's not much, but then you do some of these guys. Okay, so now what we do is we define two involutions. On these on this set of partitions. So let's call them alpha and beta. So alpha, how do we define alpha? Take the smallest, so involution 1. So what is involution, by the way? Involution is if you go A to B, then alpha A to A, then alpha square is equal to identity. So if you think of it, a partition as a permutation, then it's either identity or it's a transposition. So involution 1, you take the smallest even part to new, say, and move it. What that means is, if y to new is in delta, is in lambda. So what are these involutions? They're on the set of partitions of this type. Okay, this type meaning of with x and y and so on. So if y to new is in lambda, then replace y to new by x to new. Okay, in the partition. And if x to new, and this is the smallest, if the smallest if the smallest does not come, if y to new is not in lambda, and then obviously x to new is there, then x to new is in lambda, then replace x to new by y to new. So you get another one to get lambda prime, and this is to get lambda prime. So basically what is alpha doing? Alpha is taking lambda to lambda prime, and this is what it's doing. So for example, let's say, let's see, we have something called we have 2x1 plus y2. Here 2 new, the smallest part, and this will go into 2x1 plus x2. And if we have this thing, then obviously it will come back. So this is an example of alpha. Let's try another one where we have just x4. That will go to y4. If it was just y4, it will go to x4. So this is alpha. One more example. 2x2. Here one of these will go to y2. Okay, so you understood what alpha does? Whatever lambda is, if 2 nu is the smallest even part, if the even part comes in y, then you convert that y to x. If it's not in y, it's in x, then replace x to nu um, by y2. And it's clearly an involution. Okay, and involution 2, let's call it beta. This is the, so suppose let nu be the smallest such that y to nu or and 2 times x nu are parts of lambda. So in this case, then we replace and we interchange again. So first, if y2 new is a part of lambda, replace by y2 new by 2x new, and if
Is it, do you mean to say there x2 mu or 2 times x2 mu? X mu. Sorry.
so yeah, if let's say new is 5, then either the partition will have a y10 in there,
Yes.
or it will have two x5s in there.
Yeah, yeah, got it.
Okay. Another way to look at it is you replace all these guys by x5 plus y5 plus y5. Then you'll have two y5s and two x5s. But I'm not doing that. I'm just writing straight away. And so if y2 new is not a part of lambda, but x2 times x new is, then replace 2 times x new by y of 2. So if you remember, just recall, we were doing this kind of thing. We were saying that 1 plus 1 plus 3, and then we were replacing these by 2 plus 3 in an old proof. So we were clumping them together. And we were taking even parts and then breaking it into two parts. So we did this in bijection earlier, long back, for odd to distinct. I mean, this was all odd parts, and then whenever it was repeated, then we kept doing this, and when we kept clumping it together, it became distinct at some point. So similar idea, in fact, the same idea. Okay, so now, all right, so this is again an involution because you can go back and forth, and it may leave something untouched. If there is nothing, then you don't do anything, right? So if you take a partition and if it doesn't have a even part or nothing like that, no repeated parts, you just leave it untouched. So anyway, the question to ask is, what are the fixed points of these involutions? Okay, so alpha, what are the fixed points? Fixed points means points which don't change at all. So let's look at alpha again. You take the smallest even part, move it. If there was any part in y, if there was any part, it will have to be even part. So we will be moving it. So something, a fixed point, something which doesn't change, doesn't have any y's. And over here, if x2v is in lambda, then it goes to a y2v. So over here, there could be no even parts. So what are the fixed points? So fixed points are partitions with no y's and no even x's, i.e. only odd parts, right? And let's look at B, beta. What are the fixed points? Fixed points again, if there is a y, it has to be a y to v, right? The smallest y to v. If there is something like that, there is nothing like that. That means there are no y's. So again, fixed points are partitions with no y's and no repeated parts. Had there been 2x1, 2x2, 2x3, anything, then it will not be fixed. It will be replaced by something, right? By beta. So fixed parts are distinct parts. So X, the X partition has distinct parts, right? So what is the situation? The situation is that we have a set, um, one big set of to the same set, and then we have a beta, and both are involutions. We have and certain points which are fixed by this. So let f alpha be equal to a set of fixed points of alpha, and f beta be the set of fixed points of beta. And at this time, we you know we use the Garcia-Milne involution principle. So now I'm going to state the Garcia. So let me state the Garcia-Milne involution proof. So at this point, we invoke the Garcia-Milne involution principle. Okay. Okay. So what is the Garcia-Milne involution principle? Let C be equal to C plus union C minus, where C plus intersection C minus is empty. Okay. B the disjoint. I'm going to state a slightly simplified version, which Andrews proves. It's equivalent to whatever they have, but this is simple enough to understand. Union of two finite components C plus and C minus. Let alpha and beta be two involutions such that involutions on C such that their set of fixed points are in C plus. Okay, so lie in C. Well, he's saying lie in C. Well, obviously they lie in C. So let F alpha, respectively F beta, denote the fixed points of alpha, respectively beta. Okay. Further, suppose so um, well, I have changed the notation, have I? So what we are saying is that if you apply alpha to anything to the fixed point, then it has to be in C plus. It has to go to C plus. But if you take it to anything else, it has to go to C minus. And similarly, alpha of C minus will go always in C plus. And similarly, beta of C plus minus F beta is a subset of C minus, and beta of C minus is a subset of C plus. So what we are saying is, again, it's really the same thing, but I'm just making it over here as a separate guy. And suppose we have F alpha here, okay, and these are C plus and C minus, and basically alpha is going from here to here and here to here, and similarly beta. But F alpha and F beta stay right here. F alpha and F beta are right here in C plus. This is what we are saying. So I hope this picture is clear. Is that clear?
Yes, Professor. Professor, can you scroll up a little bit, please? Yeah.
So C is this whole set. Alpha and beta go from C plus to C minus and backwards. And the only thing is that alpha of anything here stays here. So these are the fixed points. So the fixed points, other than the fixed points, everything goes to minus and this goes to plus. And fixed points are all positive. So they're just, you actually divide them, you give a sign to them. Okay. So this is just the set of hypotheses. All right. And then we say, then what does the principle guarantee? Then the Garcia-Milne principle says, with this setting, says either a cycle of the permutation delta equal to alpha beta contains no fixed points of alpha or beta, of either alpha or beta, or so either or, exclusive or, it contains one element of F alpha and one element of F beta. Okay, so what's he saying? He's saying that when I apply alpha beta one after the other, so I take all these elements of C and I apply alpha. Let me do some other color. So you take all the elements of C and you apply alpha and then you apply beta. Okay. So let's say it was starting from C plus, you'll reach C minus and then you'll again reach C plus. Or you can start with C plus, C minus, whatever. You apply it. So what's happening is that you'll get some other element. So you're starting from this guy and you get this guy, right? So you start from this guy and you get this guy, that's delta. Okay. And that gives you a permutation of all the elements of C. It gives you a permutation. Take all the elements, take to alpha and take beta, alpha, beta, whatever. You get a permutation. Now, in that permutation, if you break it into cycles, okay, if you break it into cycles, then either it contains one element of both or it contains no fixed point. This is what it's saying. So you apply alpha and then you apply beta and then you'll get this thing. And another way of looking at cycles is that you apply alpha beta, reach here, then you apply alpha beta and you reach here, then you apply alpha beta, you reach here, and then until you reach back, and that's your cycle. Okay. And if that is the case, if this is the case, then the Garcia-Mills method gives you a approach to make a, then this tells you an approach to make a bijection, because what you're saying, you start with some element for f alpha. So you are over here in C plus, you start with an element here, and you go, alpha will do nothing to it, you go to beta, you get to C minus, then you get alpha, you know, apply alpha, then you apply beta. At some point there will be a cycle. Some point it will repeat, right? There'll be a cycle, and in that cycle, so somewhere it will come back to this guy, this point. And then in this cycle, they're saying there's going to be exactly one point in f beta. And then so you map this alpha with this beta. That's what you're doing. And if it doesn't contain any fixed point, doesn't contain any fixed point. So this is how you get the, and this is, it's because it's unique one point, you know, it contains one element of f alpha, so then it's a bijection. So do you understand what you're saying? So now let me do an example. So C minus in our case, you take set of elements where yi's, where the number of yi's is odd. I mean y2i's. And C plus with the set of numbers where the y2i's are even or 0. Okay, so we get a sign. Remember, we needed a sign over here, -1. So this is how we get a sign. We assign these guys a sign of -1, minus sign, and we assign a sign of. So let's see, what's a good example? So recall, so what were the fixed points? No y's and only odd parts. So no y's and only odd parts. Let's see, this is the guy. So this is left untouched. So this belongs to f of alpha. So okay, first of all, is it clear that our business satisfies all the conditions if we do this? Because we have fixed points and they are all in C plus, because the fixed points were no y's, no y's. No y's means you know, they were all positive, right? So all these fixed points, no even x's, only odd parts, no and distinct parts for beta, they were all in C plus. They're all in C plus because we've defined CIs where this is number of these parts is even or 0. Okay, so we apply beta to it. What happens? Well, this one is a bad example because it's also a fixed point for beta. So there is no issue here actually. Let's do something else where we have odd parts. Suppose we have this guy. Okay, now we apply beta. So beta is this 2x1 will become y2. Okay, now apply alpha. So alpha, we are taking the shortest, smallest nu and converting it into x's. So it's x2 plus x3. Now apply beta. What do we get? So beta is saying
so it remains fixed under beta.
Huh?
This is a fixed point under beta, right?
It's a fixed point,
Fixed point.
right? Okay, so now take alpha. This is the smallest. You get y2 plus. We get back here, right? Y2 plus x3. Now take beta. We'll get this 2x1 plus x3, right? Now in this, so this one belonged to, this one was a fixed point for, and in this whole story, there is exactly one fixed point, he's saying, for beta, which is this guy. So the mapping is 2x1 plus x3 maps to x2 plus x3. I mean, here we've changed the partitions to 5, but this is the mapping. So this is the biject. The bijection will have exactly one guy which is fixed for beta if there's only one guy fixed for alpha. That's the idea. Okay. So the fact that it's a bijection. Okay. So let me just write it down. Choose any lambda belonging to f alpha and apply delta equal to alpha beta repeatedly. Okay. Now there is a unique lambda prime belonging to f beta in the which lies in the cycle form, right? So lambda is the bijection. So the uniqueness guarantees that it's a bijection. So uniqueness is a bijection. So I mean, you could start with lambda prime and you will get to the same cycle, right? That's what it's saying. So uniqueness in convolution in involution principle. Okay, so yeah, we can do the proof next time. So to complete the proof, we need to proof of the involution principle. We can do next time. So let me make a remark before we leave, very short remark. This is a somewhat simplified version of the Garcia-Milling involution principle. I mean, it's equivalent. So what he's doing is that they're taking two sets A and B, and instead of the same set, they're including a bijection F and then doing this alpha beta business in this. So both sets have a positive and a negative and so on. That's so, and they have maps going from positive to here, negative to here, and so on. So they're just confusing you a little bit, but otherwise this is equivalent to this. So once you understand this, that is easy to understand. Okay, any questions?